So we have studied polynomial functions. So now let's look at another function which is called rational functions. So rational function can be written as this form. Rational function which is f of x can be written as gx over hx. Okay, so here where gx and hx, where g and h are all polynomial functions. Okay. So this f of x can be written as if this is g is an x to the n plus an minus 1 times x to the n minus 1 plus a1 times x plus a0. This is the g. If h can be written as bm times x to the m plus bm minus 1 is another polynomial plus b1 x plus b0, right? So this is the rational function, the form of rational functions. So obviously, the domain for the rational function would be all x except, because we have the denominator, right? Except those for which h of x equals 0. H of x is, what is a? H is the denominator, right? So now let's look at this example. F of x is equal to x squared plus 2 over x minus 1, x plus 2. So our denominator is x minus 1, x plus 2. So we can say, okay, so x is not equal to 1, and x is not equal. We cannot make the denominator be 0, right? So our domain is or x, if we write it as a set form, or x such that x is not equal to 1 and x is not equal to negative 2. Or you can write it as a inequality. This x is not equal to 1, x is not equal to negative 2. Or you can use the interval notation, negative infinity to 1, union 1 to, negative 2 first, to negative 2, union negative 2 to 1, union 1 to positive infinity. Okay. If you use the number line, so you need to locate 1 and negative 2. So if this is 1, so we use a circle here. Negative 2 is here, for example. So all other positions except these 2 points are in the domain. Right, are in the domain. So how to find? So this is for the domain. So what about the intercept? Since it's a function, we also want to look at the intercept also, right? We need to know the domain. We need to know the intercept. So the y-intercept, we just what? Set x to be 0. So in other words, we just evaluate f of 0, right? This function calculate f of 0. Then the point 0 f of 0 would be the y-intercept. X-intercept, we solving f of x equals 0. Solving f of x equals 0, so if f of x can be written as this one equals 0, so we cannot make the denominator cannot be 0, so we only calculate g of x equals 0, right? In other words, we just need to calculate gx equals 0. So here, our g and h, numerator and denominator, has no common factors. We need to simplify. Okay. So here we want to introduce another new thing, which is called for the rational function. We have which is called vertical asymptotes. So the vertical asymptote is the following, at least one of the following things. We always use a dashed line to denote a vertical asymptote. Okay, so if the vertical asymptote is here, if the curve will approach, this is the A, so the vertical asymptote x equals A is this one of these cases, right? When x are very close to A, this is x-axis. We don't need a y-axis, right? When x is very close to A from the right side of A, bigger than A, it will approach, the curve will approach to vertical line, but it will never intersect the vertical line. Okay? For this case, or you can have this one. When x approaches A, this is A, x equals A. From the left side of A, less than A, it will close to this dashed line, but it will never cross or touches this dashed line. Or you will have this one. Again, this is the very close to the x equals A, but never touches or cross. Or you will have this one. Okay. If one of the case is true, then we say this is a vertical asymptote. So here, when x approaches A from the right side bigger than A, so we denote it by ax approaches A plus bigger than A. Then with this function value, this is our y equals f of x, right? Our f of x will increase forever but never cross, right? So it will approach, we say it will approach infinity because it will increase forever. So it becomes larger and larger and larger. So here, when x approaches A from the left side A, so we denote it by A minus less than A. So this f of x will also approach infinity, right? Will increase. So the value becomes bigger and bigger. When x, so this case, when x approaches A from the positive and the right side of A, then this f of x will approach negative infinity. It becomes smaller and smaller, right? Forever. You can go down forever, smaller and smaller. But it will never touch, right? So we see when x is very close to A from the right side of A, then this function will go down to infinity. When x approaches A plus, f of x will approach negative A again. Okay, so this is the vertical asymptote. So here is a remark for the vertical asymptote that how to find the vertical asymptote? We say a rational function. So from this graph, so we notice that when x approaches a, it will approach infinity or positive infinity. The value will blow out. That means what? That means if the denominator h equals 0, approaches 0, very close to 0, then the whole fraction will blow out, right? So this gives the idea how to find the vertical asymptote. This is a function, a rational function f of x equals g(ax) over hx, where g and h have no common factors. We'll have a vertical asymptote at the zeros of hx. Okay, the vertical asymptote, if it's the zeros, in other words, x at x equals a, where ha equals 0. Okay, so the vertical asymptote, if x equals a, then this one will be 0, right? So it will blow out. So it's called the vertical asymptote. So here is a very important thing. This h and g should have no common factors. Okay, so it's essential to cancel any common factor before locating the vertical asymptote. This is the first, the second. It's essential to cancel or to simplify any common factors before locating the asymptote. Okay. For example, if you have this function f of x equals x squared minus 9 and x squared minus 2x minus 3. So the first thing we need to look at, if we have some common factor, so we factorize the top. X minus 3, x plus 3. So here's x minus 3, x plus 1, right? So we notice that this x minus 3 is a common factor, so we cancel out. So you have x plus 3 over x plus. So now let's locate the vertical asymptote using this one instead of using this one. Okay, so the vertical asymptote is x equals -1. Although we have some equal sign, but actually these two are a little bit different. These two graphs are almost exact the same, except one point. This graph allows x equals 3. The point x equals 3. And this graph does not allow the point when x equals 3. So these two graphs are almost the same, except one has a hole at x equals 3. The other one has no holes. This one has no holes, and this one has a hole at x equals 3. So we have the horizontal asymptote. So now let's look at another asymptote, which is called horizontal asymptote. So we say horizontal asymptote is always equal to y equals some number, b, for example, b, okay? Because it's a horizontal line, so the equation is y equals some constant, right? So which means when x is very large, approaches infinity, or when x approaches negative infinity, becomes very, very small, f of x approaches the value of f(x) will approach b, the value b. So this is the kind of vertical asymptote, horizontal asymptote. So this is the horizontal asymptote y equals b, for example. So this one, right? It can intersect somewhere, okay? But when x is very, very, very large, it will be very close, okay? It could be this one. When x is very small, it will approach this number. So we can intersect the horizontal asymptote, but remember, it should be close to this number, right? When x is very big and when x is very small. Or you can have this one, right? Or you can have this one, right? Or you can have this one, right? Or you can have this one. This is the old horizontal asymptote. Just remember, when x is very large or when x is very small, it will be very close to, approaches closer and closer to the value y equals b. So here is the remark for these two asymptotes. The first one, a rational function may have many vertical asymptotes. It can only have at most one horizontal asymptote. This is true for the rational functions. 2. The graph of rational function will never intersect a vertical asymptote, but may intersect a horizontal asymptote. Okay, so let's look at our problem. So the next question is, how do we find? So we know we can just simplify the rational function first, then find the zeros for the denominator to locate the vertical asymptote, right? What about the horizontal asymptote? Okay, so now let's look at the rows to find horizontal asymptote. Find a horizontal asymptote. So we let f of x can be written as gx over h of x, which is, this is an x to the n plus an minus 1 x to the n minus 1 plus a1 times x plus a0, right? This is the bm x to the m plus bm minus 1 x to the m minus 1 plus b1x plus b0. So when we know horizontal asymptote, that means x approaches infinity or negative infinity. So that means x is very large or very small. Okay, but when x is very large, approaching infinity or negative infinity, then the leading term will dominate other terms. So we only consider this leading term. So when m is greater than n, okay, m is greater than n, so it will approach infinity faster from the denominator than the numerator. So the fraction will approach 0, right? Then y equals 0 is, will approach 0. So y equals 0 is the horizontal asymptote. If m equals n, if m equals 0, so we can cancel out x to the n and x to the m. They are the same thing, right? So we only have an over bm. This is a constant. No matter x, how large x is, it always be at this value, right? So the function value always be close to this value. So y equals an over bm is the horizontal asymptote. If m is less than n, okay, the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptote. Let's look at example. f of x equals x squared minus 9 over x squared minus 2x minus 3. The same thing, we need to simplify first. X minus 3, x plus 3. X minus 3, x plus 1. So this is x plus 3 and x plus 1, right? So the domain, when we look at the domain is still the original one. We need to look at the original one. We cannot look at the simplified one, right? So that means x squared minus 2x minus 3, which is equal to x minus 3, x plus 1. This one cannot be 0. So the domain is all the x such that x is not equal to 3 and x is not equal to negative 1. So this is our domain. X-intercept. So we just set y to be 0. Okay, y to be 0. So when we look at the x-intercept, we need to look at the simplified one. So we set y equals 0. In other words, we set f of x equals 0. So which means x plus 3 over x plus 1 equals 0. So if you have a fraction equals 0, so the numerator should be 0, right? So you have x equals -3. So the x-intercept would be, sometimes it asks you to input the x value, sometimes it asks you to input the point. This is x-intercept on the x-axis, right? So y-intercept, we just set x to be 0, we just find f of 0. F of 0 equals what? We just plug in 0. So it would be 3. So 0, 3 would be your y-intercept. Vertical asymptote. Vertical asymptote. We need to look at this one, right? Vertical asymptote is x equals -1. Make the denominator to be 0. X equals -1. Horizontal asymptote. Let's look at the degree. This is degree 1. This is degree 1. The same degree, right? So it would be this case. So which is the coefficient of the top over the coefficient of the bottom for the leading term. So it's 1 over 1. So it's y equals 1 over 1, which is equal to 1. Okay, so now let's try to sketch the graph. So these x-intercept and y-intercept can help you to understand, help you to sketch the graph. So the first thing, let's look at the horizontal asymptote, which is y equals 1, if this is 1. So this is the horizontal asymptote. If vertical asymptote, x equals -1, -1 is here. This is 1, this is -1. So we have this one, right? So the intercept will tell you which part. It will have 4 parts, right? Which part we will have the gate, we will have the curve. X-intercept is -3, -2, -3, -3 is 0. So this must go through this point. And y-intercept is 3, 0, 3, 0, 3 is 1, 2, 3, 3 is here, right? This is -3. Okay, so our curve, I use another color. Remember, we cannot touch the x and the vertical asymptote. So I use this there. It will go through this point. Okay. So this is this example. We can sketch the graph, right? So now let's look at another example. So this time, f of x is given by 2x plus 7, x plus 2. So now we don't need to simplify, right? So the first step is always to simplify. If possible. So here we don't need to simplify. 2, we need to find domain. Domain is the denominator can be 0, so x is not equal to -2. This is our domain. 3, intercepts. So let's look at x-intercept. X-intercept is set y to be 0, so you need to calculate x plus 2. This one to be 0, so it implies that 2x plus 7 equals 0, so x equals -7 over 2. So the point is -7 over 2 is the x-intercept. The y-intercept. Y-intercept set x equal to be 0, so f of 0, which is 2 times 0 plus 7 over 0 plus 2, right? So this is equal to 7 over 2. So y equals 7 over 2. So 0, 7 over 2 would be the y-intercept. And 4, we need to find the vertical asymptote. Vertical asymptote is the one make the denominator to be 0, so x equals -2. horizontal asymptote. Horizontal asymptote would be what? Let's look at this one. This is the 1 here. This is the 1, so the same degree. So the horizontal asymptote is 2 over 1, right? Y equals 2 over 1, which is equal to 2. So now let's sketch the graph. Horizontal, 1, 2. -1, -2. This is vertical asymptote, right? And locate x-intercept 0, -7 over 2, which is here. -3 is here, right? Which is here. This is the 7 over 2. This is -7 over 2. So the graph would be right. This is our graph. If you want to draw the graph very precise, you can have more, except the intercepts, you can have more sample points. Okay, so now let's look at, so we have the horizontal asymptote and the vertical asymptote. We also, there is called another asymptote, which is called slant asymptote. Which is also called oblique asymptote. Okay, so which is this kind of line, okay, this kind of line, or this kind of line, right? Not horizontal and not vertical anymore, the asymptote. It's called oblique asymptote. So we say a function, a rational function. So let's look at the rational function. A rational function whose degree of the top of the numerator is exactly 1 more than the degree of the denominator. For this kind of case, this kind of function has an oblique asymptote. Okay, for example, we have this one, x squared minus x plus minus 2, x minus 1. Right, you can see here the degree is 2, here the degree is 1. Right, this degree is 1, so exactly 1 more. So what we should do, we need to take a long division Let's look at long division. So our x squared minus x minus 2 divided by x minus 1. So here's x, so x squared minus x. So this is the 0 minus 2, which is 0, right? You plus 0, so it's 0 plus 0, which is negative 2. So the remainder is negative 2. So in other words, so our f of x can be written as, this one is x, right? X minus plus negative 2 over the remainder over x minus 1, right? So this is the long division tells you. So this part is actually the oblique asymptote. Oblique asymptote. Okay. What does this mean? This means when x is very large or very small, then this part will approach 0, right? So it only approaches x. So our domain is, still need to look at the domain. Domain is the denominator cannot be 0, right? X is not equal to 1. Y-intercept is x equals 0, so f of 0, plug in 0, 0. So it's negative 2 over negative 1, so which is negative 2 over negative 1, which is 2. So the intercept is 0, 2. X-intercept is set this f of x equals 0. So in other words, we have x squared minus x minus 2 over x minus 1 equals 0. So the numerator to be 0. We cannot simplify, right? So the numerator is x squared minus x minus 2 equals 0. So you have x minus 2, x plus 1, right? There is no common factors, so we cannot simplify. So this is x equals 2, x equals negative 2, negative 1. So you have 2 points, right? X-intercept. X-intercepts 0, 2, 2, 0, and negative 1, 0. So now let's try to sketch the graph. Okay, horizontal asymptote. Horizontal asymptote, which is make the denominator to be 0, so x minus 1 to be 0, right? So the denominator equals 0, so x equals 1. This is the vertical asymptote. I made a mistake. This is the vertical asymptote. This is vertical horizontal asymptote. Since our degree, the top is greater than the degree of the bottom, so m is greater than n is greater than m. So we're using this rule. This rule tells you that if the denominator is less than the numerator, the degree, no horizontal asymptote. So we have no horizontal asymptote. So we have oblique asymptote, which is y equals x, right? As I said, this part is the oblique asymptote. So our graph would be, so the first thing we still need to locate our asymptotes first, right? Locate the asymptote. So vertical asymptote, x equals 1. 1 is here, for example. This is 1, so x equals 1. We have another oblique where x equals y. X equals y line. Right, this is x equals 1. This is x equals y. Y equals x. And we need to go through the point 2, 0, 1, 2, 2, 0. And we need to go through the negative 1, 0, negative 1, 0. right? This is 2, this is negative 1. We also need xy intercept is 0, 2, 1, 2, 2 is here. Okay, we need to go through these 3 points, so we have the curve would be, looks like this one. Okay, never cross the vertical asymptote. So this is our curve.